The reaction of zinc with copper sulfate did not require the addition of energy to make it proceed. Such reactions are said to be spontaneous. Note that once the electrons from the zinc strip turns the copper ions into copper metal, the copper metal doesn't lose electrons to be gained by the zinc ions to turn them back into zinc, as would be the case if the reaction was reversed. It seems then that copper ions cannot reduce zinc. That is, the zinc metal is a stronger reducing agent than the copper atoms. Or, put another way, the copper ions are a stronger oxidizing agent than the zinc ions. By performing similar experiments with other substances and other ions, chemists developed a table placing the atom or ion that most readily gains electrons, that is, most readily reduced, and thus the strongest oxidizing agent, at the top left, and the substance that most readily loses electrons, that is, the most readily oxidized, thus the strongest reducing agent, on the bottom right. And if you think that seems unnecessarily confusing, I would tend to agree. Having this organized in your mind, though, is really important. Anyway, having the equations arranged this way, it is easier to confirm spontaneity. The equations as shown here are referred to as half-reaction equations, because two half reactions are required to form one reaction equation, such as the copper ions reacting with the zinc metal. An imaginary line drawn between the strongest oxidizing agent and the strongest reducing agent in the top left bottom right orientation as shown here indicates spontaneity. Put another way, the reaction is spontaneous if the oxidizing agent is positioned above the reducing agent in this table. A bottom left top right orientation indicates the reaction is not spontaneous. The oxidizing agent is below the reducing agent. Zinc ions will not react spontaneously with copper metal, and experimentally this is confirmed. Written like this, we can predict spontaneity as well as clearly seeing the two half reactions that make up the total reaction. We properly balance each half reaction by adding in the necessary number of electrons to turn the reactant into the indicated product. Here there is no doubt that each half reaction is a reduction half reaction, and the gaining of electrons is clearly indicated. Your data book has a page of reduction half reactions arranged in exactly the same manner. The oxidizing agents on the left of the page and the reducing agents on the right. The strongest oxidizing agents are on the top left, and gradually losing the ability to gain electrons as you go down the page. The strongest reducing agents are at the bottom right, and having an increasingly harder time losing electrons as you go up the page. Let's look more closely at this table and see if we can find the copper ion and zinc ion reduction half reactions. Ignoring the voltages on the far right for now, you will learn what roles they play later in this unit. See if you can find the copper ion and the zinc metal, the reactants in our net ionic equation. The copper ion is the oxidizing agent and gains electrons. This table indicates this as you follow the half reaction from left to right. Copper solid is a product. The zinc solid is the reducing agent and loses electrons. Again, this table indicates this as you follow the half reaction this time from right to left. The equilibrium arrows in these half reactions show that equations can be read left to right or right to left. If the equation is read from left to right, it is a reduction half reaction. Read from right to left, it is an oxidation half reaction. Zinc in this case is oxidized. It loses 2 electrons. And this is clear in an oxidation half reaction because the 2 electrons lost from the zinc solid are shown as products. I want you to be also aware many redox reactions occur in an aqueous solution, and that the water itself could react with one of the reactants. According to your table of reduction half reactions, water is both an oxidizing agent, as shown here, and a reducing agent, a little higher up than this image shows. To determine if water does indeed react, we note the position water exists in this table relative to the other reactants, copper 2+ ion and zinc solid. Only if the oxidizing agent is above the reducing agent does a reaction occur. Water, as an oxidizing agent, is below the zinc solid. And if you were to check your own table in your data book, you would see that the copper 2+ ion is below water if water were the reducing agent. Recall that a bottom left, top right orientation of reactants in this table indicate a non-spontaneous reaction. The top left, bottom right orientation of reactants in this table clearly indicate that this reaction is spontaneous. It's worth noting that your text shows a slightly modified procedure for determining reaction spontaneity. I find it easier to only consider the reactants of an equation and their positions relative to each other in the table of reduction half reactions in your data book. Additionally, your book doesn't mention that water could play a part in redox reactions in an aqueous environment. What if copper ions were reacted with aluminium metal? Both water and the copper ions would gain electrons from the aluminium atoms, and in reality this is indeed the case. But in this course we only consider reactions between the strongest oxidizing agent and the strongest reducing agent. So one extra step I would add to your text when writing and predicting the spontaneity of redox reactions is to first write out all the reactant species present, remembering to dissociate all soluble ionic compounds and ionize the top 6 acids, and write out water if the reaction takes place in an aqueous environment, before identifying the strongest oxidizing agent and the strongest reducing agent. Some of the questions in your text explicitly state what the reactants are, but you should not expect that luxury in any of your exams.